Okay, we are beginning new topic today, which is differential equation, and there is very little theory that we need to do for this. And after it's different types of differential equations and how do we solve. Basically, learning the tricks and techniques of solving differential equation. But before we acquire that knowledge, we need to understand what do we mean by differential equation. Are they really going to be useful to us in solving our day-to-day problems? And how do we figure out the theory and what are the different methods? What is going to be the theoretical support? And more than that, what we will try to understand is differential equation is going to be purely something like algebra. You deal with those equations, solve them, and eventually you will get the functions. But we would also like to see what is the geometry behind the algebra which is happening. What do we mean by a differential equation, and what do we mean by solution of that differential equation? So in 8th standard, 9th standard, we have studied p of x, polynomial in x, which is say x square minus 5x plus c is equal to 0. P of x is equal to 0. And we were supposed to find out the solution set of this. This was polynomial equation, quadratic equation. Okay. So when we solve any type of equation, we end up getting the solution set. We get the values of the unknown or maybe variable, which eventually satisfies the given equation. If it is polynomial equation, the solution set satisfies polynomial. If it is trigonometric equation, we find out the values of angles theta. Those angles, if we substitute back in that equation, we satisfy trigonometric equation. There could be matrix equation, the next topic that we are going to learn. There could be vector equation. So you find out the vector, put it back into the original equation, and that satisfies the original equation. Similarly, these are differential equations. Basically, the equations which involve differential coefficients. Differential coefficients means something like this, dy by dx, something like d2y by dx squared, and so on. If the equation is such that it has got the derivatives also involved in that equation, and we are expected to solve that, that means here it is little complicated because we are, see, if a function is given, you can easily find out the derivative of that. And it is what we are trying to do now is in the opposite direction. So it is essentially going to be something related to antiderivative. But then the condition which is given to you, the equation which is given to you, which we will call differential equation, suppose we are successful in solving that differential equation, then we will end up getting a function. So we will end up getting a function y as a function of x. That is what we will call the solution of differential equation. But it is not only that, because the moment we say function, we need to know domain. So if we solve differential equation, we also should find out the domain of definition of the function that you will say that as a solution of differential equation. Of course, you have to find out the function, and moreover, the third thing which is required, this is first, this is second, that means you find out domain, you find out the function such that for every x in the domain, this function is satisfied or it is valid. And the third thing which is most important is that in this domain, this function must be differentiable. Because If you end up finding out some function which is not differentiable in the domain that you have found out, then the differential equation itself will fail, because differential equation will have these coefficients, and if the function is not differentiable, it does not make any sense. Therefore, essentially solving differential equation is three things: one, finding domain; two, finding the function; and three, checking the differentiability of that function in the desired domain. And therefore, it might be possible that you may end up getting more than one functions who satisfy the same differential equation. We will see the examples of that kind. So, what we will learn to solve is maybe it is a solution of the differential equation. It could be a solution of the differential equation. That means there could be several solutions which are possible. Okay, so this is the background. What do we mean by differential equation and what is solving differential equation? I have explained. Another terminology that you need to remember, maybe in 12th standard board exams you have questions on that. That is order of differential equation and degree of differential equation. Order and degree. Okay, order of differential equation is order of the highest differential coefficient. So if a differential coefficient is d2i by dx square in the differential equation which is given to you, then it is second order differential equation. Degree, I mean order of the differential coefficient is 2. If only dy by dx is present, everything else x or y are constant, then it is going to be first order differential equation, because order of highest differential coefficient is 1, and so on. So order means order of highest differential coefficient, and degree is the power of highest differential coefficient. So degree meaning, I mean, it is easy to remember. Degree of this polynomial is 2 because that is the term, that is the highest power term whose coefficient is non-zero. Similarly, degree of differential equation is the highest power of the highest order differential coefficient. Is it clear? And we will have some examples and try to learn it. Now, typically there will be differential equations. हाँ बोला श्लोक. तुझा माइक जरा ठीक करा झाला, ऐकायला येत नाही पटकन. Okay, we will come back to that. At that time you ask question about degree and order.
सर मी म्हटलं की ऑर्डरची डेफिनेशन मध्ये एकदा सांगू शकता?
Order of differential equation is the order of highest differential coefficient. Okay. Y dash is equal to f of x comma y. This is one way of expressing differential equation. We will call this as explicit. But it might not be always possible to express differential equation in this form, where differential coefficient is in LHS and maybe only one, and the relationship of x and y and maybe constant in RHS. Explicit, you can separate differential coefficient from the rest of the equation. explicitly defined differential equation. And the second way of expressing differential equation could be, it is a function of x comma y dash is equal to 0. So there is a relationship which is given to you, which is of the kind x, y dash, and RHS is kept 0. And it is impossible to separate only differential coefficient in one side and a rest of the equation on the other side. This is implicit. Okay. So finally, it is all about having differential. So for example, how will an equation, differential equation look like? Simplistic, maybe dy by dx is equal to x minus y square. This is explicit type of example. Dy by dx is equal to y minus x square, something like that. Implicit example, if I want to write, I can write by looking here. Implicit d2y by dx square bracket square plus dy by dx bracket cube is equal to e raised to x, something like this. Okay. Now, it is not necessary that whatever differential equation you have written, we will be always successful in finding out the solution of that. Maybe we can, maybe we cannot. And the theory of indefinite integral, we have answered those questions there. Will antiderivative exist every time? Will we be able to find out, etc.? And if we find out, will it be unique? These questions we have answered while learning indefinite. Those are the valid questions for differential equation also, because if I want to go back to function, this is what suppose is the equation, and if I really want to find out how y is related to x, solving differential equation, finding domain and checking differentiability, then it is of course finding out indefinite integral, antiderivative, and get to know what your function is. So this is little more complicated search operation which we are going to do. And maybe this is extremely difficult. This is difficult to solve. Maybe may not be able to solve. This is extremely simple to solve. So almost they look alike, but as far as solution is concerned, substantial difficulty level in solving them. Okay, so this is how the differential equations are going to look like. Now, if I have, this is order 1 differential equation I have demonstrated here in the implicit example. If it is order 2, then it will look like this. F x will be there, y will be there, y dash will be there, y double dash will be there, is equal to 0. So this is differential coefficient. When I said I dash, it is dy by dx is present in the equation which is provided to you. When I say y double, d2y by dx square is available in the differential equation which is given to you. Okay. And okay, we will go ahead and discuss. So first lecture, I would like to give you an idea about how differential equations algebraically, what do they mean, and what is their corresponding geometric interpretation, and algebraically what is the solution of differential equation, and what is its corresponding geometric interpretation. And therefore, the first equation that I would like to take is going to be of first order. So it is going to look like y dash is equal to f of x y, x comma y, which is something like dy by dx is equal to f of x comma y. If we take this example and understand what we are trying to do geometrically, it will give us clear picture. What is dy by dx? Suppose there exists a function y, which is function of x. Then the meaning of dy by dx is the slope of tangent at that point or at any point x comma at any point x corresponding point y. Okay, so dy by dx is basically the slope of tangent at x naught comma y naught. You substitute at your point and you will get the slope of tangent there. Okay, and then if I substitute the same point, this is LHS, slope of tangent, and if I substitute the same point in RHS, f of x naught comma y naught, I will get the value of that slope. Array, do you understand? Suppose dy by dx is equal to x plus 2y minus 3, suppose. And then at x comma y equal to 1 comma minus 2, I want to find out the slope of whatever that function is. We don't know what that function is. Unless we solve this, we will not come to know what the original function is, whose differential equation looks like this. But suppose if we solve and try to plot, then at x comma y, which is 1 comma 2, if we try to draw the tangent to that curve at 1 comma 2, we will get dy by dx at 1 comma 2, which is going to be equal to 1 minus 4 minus 3 is equal to minus 6. At 1 comma minus 2, you will have a slope of tangent. This. It also means at 1 comma minus 2, the function is going to be differentiable. There exists a unique tangent. And minus 6. If you put some other point 0 comma 0, what is the tangent? Slope of tangent at origin, it will be minus 3. And so on. Therefore, using this information, I can always plot. Suppose geometrically I have x-axis and y-axis with me. And if I take 1 comma minus 2, 1 comma minus 2 was here. 1 comma minus 2 was here. And I was given that the slope comes out to be minus 6. So approximately, if I draw a small segment here, whose slope is minus 6, I will get an idea that whatever that curve is, if it comes here, it is going to be tangent and move it like this so that the slope of tangent is going to be minus 6 at that point, which is very good. So we will call this XOY plane a direction field. Direction field, if we call that, it is equivalent to your differential equation. Differential equation in algebra is same as direction field in geometry. And therefore, either we can write a computer program by which at every millimeter or at every 5 millimeters, 5 by 5 millimeters square or lattice points, you get to know what is the direction of the tangent, what is the slope of the tangent, and you define at that point, you draw a line segment whose length is also 4 millimeters. If we write a computer program and run it, within no time, you will come to say minus 10 of x to plus 10 of x, and corresponding values also. On y-axis, you can put So the differential equation corresponds to direction field in geometry, and if we are successful in solving this differential equation, it will look like y is equal to some function of x, which is a solution of differential equation in algebra, which will correspond to, you will end up getting some curve, something like this eventually, or maybe family of curves like this, that we will experience today by taking couple of functions. Then the curve that you get is called integral curve. So integral curve is geometry, y is equal to phi of x is algebra of differential equation, and corresponding higher level direction, that is the existing xy plane that in which we are going to work, is a direction field geometrically, and corresponding algebra is the given differential equation. Okay, I pause the video, I check whether you have understood up to this point. And many a times this graphical solution of differential equations become very important, especially when the differential equation is extremely difficult to solve algebraically. Okay, and let us try to understand this by taking first example.
Excuse me, sir.
Yes, Harshita.
Sir, in the graphical method, how would we?
Okay, the question is, how do we know whether this point 1 comma minus 1 minus 2 lies on the required curve or not? Very good. Now, suppose we have a differential equation and we solve it. dy by dx is equal to f of x comma y, and if we end up solving it, we get something y is equal to phi of x plus c. We will get y is equal to phi of x plus c because we are practically finding out antiderivative, and therefore this constant of integration will always be there, and that is your unknown. So unless and until we get a specific condition, suppose you want to find out a specific curve, then you need to have some specific condition which we put in this and get the value of c, then your curve will be uniquely defined. But if you do not have a specific value for getting a particular solution, we will say that as a particular solution, or if we have this c with us, it is a general solution. So if this c, which is a parameter which exists there as c, then it is a family of solutions. It's a family of solutions, and for every c you have one curve. Which c are you talking about? The moment you specify which c, your integral curve is fixed. That is going to be the unique solution for the given condition and the given differential equation. Is it clear, Arshita?
Yes, sir.
And moreover, if the order of differential equation is 1, no, I should not disclose this at the moment. Let's face the situation and I will explain you that later on. Now, so the first example is dy by dx is equal to minus x upon y. Okay. Now, before you start doing it, I will give you sufficient time to sketch the direction field. But before that, let us analyze. If this information was given to computer and ask computer to find out the slopes at different points in XY plane, what computer will do? Computer will have program to pick up the points in random or with some logic on x-axis first, 1, 0, 2, 0, 3, 0, 4, 0. Computer will pick up a point, it will substitute that value here, find out the slope, give you the slope at that point. Maybe if you further program it, you will, I mean the computer itself will go to the direction field, and at that point 1 comma 0 it will sketch vertical or a line with slope 1, slope 2, whatever. Do you understand? So suppose 1 comma 0 is put here, the slope is going to be undefined. Therefore, if computer will go and sketch a vertical line there. If it is 1 comma 1, 1 comma 1, then the slope is minus 1. So computer will go and sketch a line at 1 comma 1 of the slope minus 1. Something like this computer will do. But when human being is trying to do the job, we will not do it that way because we really do not know what are we doing. There are many points in the plane. What we will do is, we will say dy by dx is equal to minus x by cy is constant. I mean, it is the value of the slope and it is constant c, and therefore I get a relationship that x plus cy is equal to 0. Or maybe if you want the equation of straight line, y is equal to minus x by c. Okay, and then you will try to find out all the points in the plane having slope c. Now let me demonstrate. Having slope c. Suppose I have y-axis, it is bad. Suppose I have y-axis and x-axis, and suppose c value is say, equal to 1. Slope I want equal to 1, case 1, slope 1. Then my equation is x plus y is equal to 0. So I know this line, might as well I know this line in xy plane, and therefore I draw y is equal to minus x, therefore I draw a line like this passing through origin, and every point on this line will have slope 1. So I will draw my segments, my segments perpendicular to this line like this. Whatever number of segments you want, you can draw. At 45-degree positive slope on this line, the point is the point of intersection, and the slope at that point is going to be this except 0, because we don't know what happens at 0. Okay. Now this orange color line which I have drawn is such that it has got all the points giving slope 1 of the giving the slope 1 of the given curve, and therefore it is called isocline. Same slope line, isocline. So if in this case, in this problem, if c is equal to 1, I could get one isocline. Now in each quadrant at least 3. So 3 this way, if you use 3 plus 3, 6 plus xy plane, 6, 7 and 8. So draw 8 isoclines and decorate them the way I have decorated the first isocline, and let us see how our direction field looks like. So if we take value of c is equal to minus 1 now, minus 1, then y is equal to x is going to be our isocline. Value slope of isocline, and segments will look like this. It is good in this particular example that the tangent segments are perpendicular to the isocline, because if you see slopes of both of them, product of the slopes is minus 1. Okay. Then I draw somewhere here. For different values of C, you can always lines, and if you decorate them with the slope segments, of course, we have on y-axis what will be the value of C? Uh, x is equal to 0. That is what. So value of C is going to be 0. That is how the direction field is going to look like. On x-axis, there will be vertical lines and so on. Just let me complete this diagram so that we will be able to see some curve which is emerging out of this business, and you get to know what is that curve. It is like at every point the curve is coming and the tangent is making sure that the curve will not intersect that point and it will go tangential to that point. So therefore, if you look at it, this is going to be a circle and there will be concentric circles. Concentric circles which you will find will be visible more number of isoclines you draw, and it is very easy differential equation to solve. It will give you x square plus y square is equal to constant, some constant, and they are all concentric circles with different values of C. You will keep getting different circles. So this is a parameter which I was talking about. If you fix C, you get a particular solution. So concentric circles is the solution of this differential equation. We got it not by solving but by geometry method, and it was easy. So let me give you one more problem to sketch, which unless you sketch, it is not going to be visible how the curve is going to look like. Okay. The problem is y dash, example 2. Try to do the same thing, whatever we have done for the first example, and show me how your notebook looks like. Try to solve it. Suppose I have y-axis and I have x-axis. For C is equal to constant, C is equal to 0. Then we get the equation y is equal to x plus 1. And y is equal to x plus 1. Suppose it looks like this. This is the isocline on which I am supposed to draw the tangent segments having slope 0. Like this. Like this, at least we have to draw 6 isoclines and draw corresponding tangent segments on those isoclines. So I will call this as C is equal to 0. Okay. So I will complete that activity quickly. So this is how the picture is going to look like. You take 4 or 5 or 6 different isoclines, and it is quite visible now that your integral curve, suppose it enters from here, this is -2 slope. So it is entering like this, and then the moment it touches it goes to the second, it will also throw away, then it will go here, then it will again throw. It is not allow, these green segments will not allow the curve to cross. And then here, if it enters this corridor, c is equal to 0, c is equal to 2, then the curve is supposed to be asymptotic with respect to c is equal to 1. So these integral curves are going to be going like this. All are going to be distinct. They will not intersect each other, nor they will intersect the line c is equal to 1. Okay, the curve is going to enter like this. What will happen from the other side of c is equal to 1? Similar. It will go like this, it will go like this, it will go something like this. The moment it enters the corridor, it has to follow. It cannot come back, because if the curve come back, it has to change the slope. So it is like this. Enters and keeps becoming asymptotic. This is how direction feed is going to look like. This is how your direction feed is going to look like. We do not know. This could be a very complicated solution. However, here I would like to show you one very interesting fact, that you concentrate on this line where the isocline, slope of isocline and slope of tangent segment is exactly same. So this is a special line which actually itself is a integral curve. So c is equal to 0, no, c is equal to 1, c is equal to 1 वाला जो line है, that 1 plus x minus y is equal to 1. Thus this itself is the solution of differential equation. 1 gets cancelled, y is equal to x. Yes, y is equal to x is a solution, because dy by dx is equal to 1. So if you substitute this value of dy by dx in the original equation, 1 is equal to 1 plus x minus y, you end up getting y is equal to x back. So this is a special solution, a particular solution. It is not a family of solutions, it is unique, and hence it is a special solution. So we directly got one solution of this differential equation. However, all the remaining solutions are not going to be that easy, because this is not variable separable. So remaining solutions of this differential equation will have y is equal to f of x kind plus c, and this c parameter is giving you all these curves. For different values of c, you will keep getting different integral curve. And what is going to be so special about the function, that we will get eventually, that it is going to be asymptotic to this line. Which line? C is equal to 1. C is equal to 1, it will never intersect. All these curves will never intersect c is equal to 1. And they will become asymptotic. As your value of x increases, they will keep on coming closer and closer, but will never intersect. This is how the interpretation of integral curve and the solution of differential equation is. Now, these are the two examples which we have taken where everything was fine. That means at every point we were able to find out the slope of the curve, etc. However, there could be situation where you might not be able to find out the slope itself. It's confusing. So let us just note which are the kind of cases where we will not be able to really draw a green segment which gives me the slope. Number one, it is possible that your integral curves or solutions of differential equations are like this. in XY plane. There are one family is like this, another family is like this. It is always possible that you end up having solutions or integral curves like this, and in that case, if you try to find out what is the slope of tangent at this point or at any point of intersection of the two curves, you won't be able to get a specific value of tangent, because at that point there is a problem in drawing tangent. That means differentiability at that point is not available. So if the curves intersect, then we might not get the slope at that point. That is one situation. And it is another thing which we must know, that it is not going to be possible that at one particular point, there are two families. One family is like this. So at this point, there exists a tangent to that family, and with this slope, and there exists, suppose, another solution of differential equation such that it is a different family, but it is tangent at this point. It is different family but tangent at that point. So at any point in this direction field, it will not happen that two curves are sharing the tangent. It will not happen. Two curves cannot be tangent or touch each other at one particular point in the direction field. These are the two cases we must be aware of while drawing the integral curves. So let me have one example where there could be a couple of points, or a point or two, or a line or something like that, where you won't be able to calculate the isocline and you won't be able to decorate. The example is key examples dy by dx is equal to example 3. Dy by dx is equal to 1 minus y upon x. Now don't spend much time on this, just figure out which are the specific points or special points where getting the slope is not possible, and maybe try to sketch very quickly. If we follow our procedure, what is going to happen is this is equal to c, and therefore 1 minus y is equal to cx. Therefore y is equal to 1 minus cx. Y is equal to 1 minus cx is going to be our equation for drawing isoclines for different values of c. So if you start, c is equal to 0 if you put, y is equal to 1, y is equal to, c is equal to 0 if you put, y is equal to 1 is going to be your isocline. Okay. If c is equal to 1, then minus x plus 1, that is minus 1 slope passing through 1. So if c is equal to 1, this is your isocline. C is equal to 2, y is equal to minus 2. It is going to be this your isocline. C is going to be half. This is going to be your isocline. And so on. For different values of C, this is 2. C is equal to minus 2. C is equal to minus 1. Something like that. C is equal to minus half. So these isoclines are concurrent at x comma y. uh, 1 comma 0, and therefore definitely differentiability is lost at that point. This is the point where it is not differentiable. What is that point? 0 comma 1. And why? Because it is indeterminate. The slope is indeterminate. dy by dx is equal to 0 upon 0. That is why we are obviously getting a point in this direction field where we cannot draw green segment. Moreover, y-axis itself, if x is equal to 0, then the slope is undefined, and therefore y-axis itself will never become the isocline. So, I mean, that is what is the implication. Y-axis will be free. We will not have any isocline. Y-axis will not be having any green segment. That is what y is equal to 1. Okay. So that is what is the special case which I wanted to demonstrate, and you will see that drawing these integral curves or drawing this direction field will give you fair idea about how the integral curve or solution of differential equation going to be. This is really useful in financial calculations. Also, you end up getting many differential equations which are not easy to solve. So if you write a proper program by which you get the direction field, then by for specific value of x, you can get the curve very easily and quickly fixed. And therefore, this method of solving differential equation is not there in our syllabus, but still we are learning geometric interpretation. And maybe if you get into IITs, second, third year of IIT, you may have some exposure to this. Okay, now let us begin with algebraic tricks and techniques. Before that, I would like to write down what is the meaning of solving differential equation. Let capital A be subset of R square. Let f be defined from A to R. Let I be subset of R. Function phi defined from I to R is said to be solution of differential equation dy by dx is equal to f of x comma y explicit or f of x comma y dash is equal to 0 implicitly defined on I if and only if phi is differentiable on I, and for every x belonging to I, x comma phi of x belongs to A, and phi dash of x is equal to f of x comma phi of x. So the three conditions that we were discussing are put here proper. That is the meaning of solving differential equation. Okay. You may just note it down if you have understood. There is no need to remember this, but this is what is systematic approach. Now, here, if dy by dx is equal to g of x upon h of y is a differential equation, then its solution is h of y is equal to g of x plus c, where h and g are antiderivatives of h comma g. This is typically variable separable method of solving differential equation. Very useful. The proof of variable separable we are trying to write down. Without wasting much time, let me write down the proof and you may copy it. Meaning of solution of differential equation implies for every x belonging to I, we have y is equal to phi of x, such that phi is defined from I to R and phi dash of x is equal to f of x comma phi of x, implies phi dash of x is equal to g of x upon h of phi of x for every x belonging to I. This implies you can always cross multiply phi dash of x into h of phi of x is equal to g of x. So now this is the situation where you can take integrals on both sides, integrating both sides, or you can write this as d dx of capital H of phi of x is this quantity. If you differentiate capital H of phi of x, you get this. That means indirectly I am integrating, which is d dx of capital G of x, and then if I integrate both sides, I get h of phi of x is equal to g of x plus constant of integration. That is what we were supposed to do. So for all practical purposes, you cross multiply h of y dy is equal to g of x dx. You cross multiply those and take integrals of both sides. You will end up getting h of y, which is equal to g of x plus c. That is precisely what this is. So with this explanation, meaning of solution of differential equation, and it is just a cross multiplication and showing that chain rule is applied here, and therefore I can always say that it is d dx of capital H comma phi of x, and then integrating both sides with respect to d with respect to x, you get rid of this derivative sign and you get constant of integration. This constant of integration is going to give you a family of curves every time. So it's a general solution every time. And if you are interested in a particular solution, for a specific solution, you need some condition, initial condition, t is equal to 0, something like that. Okay, now I'm not interested in conducting the discussion about the degree and order, which you should solve few problems on that and get to know. Now, having learned the proof of variable separable method, let us try to solve some problems. Break. First problem, question 1, x plus y divided by dx minus 1 is equal to 2 e raised to minus y is equal to 0 when x is equal to 1. Solve differential equation is the heading always. Correction. Students are taking more time, that means I have made some mistake. It has to be x plus 1. Do it again. X plus y divided by dx is equal to 2 upon e raised to y plus 1, which is equal to 2 plus e raised to y upon e raised to y. अरे परत मी इथे y काय माझं झालंय and therefore you straight away cross multiply and write it e raised to y upon 2 plus e raised to y dy is equal to dx upon x plus 1. Now you can, using variable separable, you can integrate this, integrate plus c, or let us write it after taking the integration. What is the integral of this? Log of 2 plus e raised to y is equal to mod log x plus 1 plus log c. If you simplify this, what you will get is 2 plus e raised to y is equal to c into x plus y. Given condition is y is 0 when x is 1. You substitute y is 0 when x is 1, you get 2 plus y is 0, 1 is equal to when x is 1, y is 0, c, 3. So we get 2 plus e raised to y is equal to 3. X is equal to 0, x is equal to 1, so it is 2c. Therefore c is equal to 3 by 2. Something like this, and therefore the final answer is e raised to y is equal to 3x minus 1 upon 2. Now you may cross check by differentiating this and checking whether you end up getting the given or differential equation or not, but then it is going to be. Example number 2. Y inside bracket 1 plus log x dx by dy minus x log x is equal to 0. Y is equal to e square when x is equal to e. Okay, answer for this question is y is equal to ex log x. Let me know if you want me to solve, but otherwise, question 3, cos dy by dx is equal to small a belongs to real numbers and y of 0 is equal to 2. Answer for previous question, cos y minus 2 upon x is equal to 1. Next problem, method of substitution. Problem is 1 plus dy by dx is equal to cosec x plus y. You need to do some substitution and convert it into variable separately and solve. Put x plus y is equal to t. Therefore, 1 plus dy by dx is equal to dt by dx. Is that right? And therefore, dy by dx is equal to dt by dx minus 1. If we substitute back in the original equation, we get 1 plus dt by dx minus 1 is equal to cos t. This gets cancelled, therefore sin t dt is equal to dx. Integrating both sides, correct? No? Dt sin t dt is equal to dx. Integrating both sides, you get x is equal to integration of sin t is minus cos t plus c. That makes it x plus cos x plus y is equal to c, or minus c is equal to 0, or plus c is equal to 0. It is a constant of integration. Problem 4. Question 5. X plus y dy by dx is equal to sec x square plus y square. Solve. Answer for this is sine of x square plus y square is equal to 2x plus c. Question 6. Last question. Question 6. And I think the type is also getting over. dy by dx is equal to 4x plus y plus 1 bracket square. Check. What is the solution? Okay, the substitution in this is this bracket, and then immediately you get variable separable. The answer for this is 1 upon 2 tan inverse 4x plus y plus 1 upon 2 is equal to x plus c. Okay. So that is where we are going to stop for the day. These are some elementary differential equations that we have solved today. However, the geometry part of differential equation is very important for understanding what exactly are we trying to do.